Here, as you can see, is project on multisim. The circuit is already set up with multimeters to measure the different electrical components. So you have multimeter 1, 2, 3, and 4, and they are shown, the values generated on them are shown below here. So you set up the multimeter, the first one, in series with the voltage source to get 1.652 milliamps, and it's in series with the voltage source because current in series is constant. So next you have the second multimeter in the parallel component R2 and R3, and it's connected end to end to the R2, so that to show the current that's flowing through R2, and here it gives you 747.564 microamps, and for our I3 it's connected end to end with R3 to give you 901.057 microamps, and the current entering that's I1, that's a KCL, Kirchhoff's current law. Current entering at the node is equal to the current leaving, so I2 is equal to I1 is equal to I2 plus I3, sorry. And you can see in the calculation here, if you add 747.564 plus 901.057, you'll get 1.652 milliamps, somewhere about there. And also you can find the current in the circuit by finding the total resistance in the circuit and using the multimeter again, and then by using Ohm's law, which states that current is directly proportional to the voltage held at a constant temperature, and the formula V equal IR. So the total current will be equal to I equal V over R, 20 volts over the total resistance in the circuit, and that would be generated by the multimeter to give the total resistance, which that's not done, but you would connect the positive end to here to get the multimeter to get the total resistance in the circuit. And secondly, to find V, the voltage across R1. Okay, here I've connected the multimeter across R1. It looks weird, but the multimeter is connected in across R1 to give you the voltage across R1, and the voltage across R1 would be 16.486 volts. And to find voltage, you have to connect the voltmeter, the multimeter here across R1. The voltage across R2 and R3, because they're in parallel, the voltage across any one of them will be equal. So the voltage across R2 or the voltage across R3 will be equal to 3.514 volts, shown by the voltmeter reading here, as in parallel voltage is constant. It could be also found by the value we got for I2. That's the value we got for I2. Sorry, this value times the resistor R2, 4.7 kilo ohms, which will give you a value relatively close to the 3.514 volt. That's how it could be calculated, as due to Ohm's law, V equal IR.
Okay, so alright, we have a signal generator here set to the values of 2 kilohertz for the frequency 6 volts for the amplitude and 0 volts for the offset. And right here we have the oscilloscope, which show us the waveform and how it is produced. Right on the scale right here we have 500 microsecond per division and 5 volts per division. So this is what the waveform would look like on the oscilloscope with these values inputted in the generators.